All right, thank you all for coming, and thank you again for IPAM and the organizers for the invitation to give a talk. So today's talk is about the interface between machine learning and dynamical systems, and illustrating how reproducing Kernel Hilbert spaces can represent a good mathematical framework for this interface. And this is mostly for the direction machine learning for dynamical systems. So this work started about 10 years ago. So this is like joint work with the following collaborators. And my talk will be mostly a summary of different results. So I'll just start by defining the terms in the title. So what is the theory of dynamical systems? The theory of dynamical systems addresses the qualitative behavior of dynamical systems as understood from models. So here we are interested in general, the long-term behavior. So not necessarily with prediction, but we are interested in other properties of differential equations, whether they are autonomous, controlled, or stochastic, or they can be also discrete time or continuous. So this theory is model-based. On the other side, we have the machine learning, which is concerned with algorithms designed to accomplish a certain task whose performance improves with the input of more data. So this is not model-based, but so it has direct access to the data. So in some sense, there is a sort of complementarity between the two fields. So one is model-based, so it comes from a certain understanding of the system. The other one is more direct because we are basing our analysis on data. And the intersection of the two fields is largely unexplored, and I think it's very interesting field. So here we'll have two directions mostly: machine learning for dynamical systems, where the goal is to develop a database theory of dynamical systems. So instead of having a model-based theory of dynamical systems, where we are interested in analyzing the qualitative behavior of dynamical systems based on model, we'll be interested here in a database theory, which is like a sort of model-free qualitative theory of dynamical systems. The other direction is dynamical systems for machine learning, and the goal here is to view algorithms of machine learning as dynamical systems and then analyzing them using tools of dynamical system theory. So the point here is mostly to focus on the direction of machine learning for dynamical systems. So as I mentioned, the goal of this work is to combine between the tools from the theories of dynamical systems and machine learning in view of database qualitative theory of dynamics for analysis, prediction, and control of nonlinear systems. So the approach is to work on reproducing Kernel Hilbert spaces, which are often viewed as linearizing spaces. So here, linearization means that we are going to map a nonlinear system into a higher dimensional, possibly infinite dimensional reproducing Kernel Hilbert space, where linear system theory will be applied. So it doesn't mean that we are going to assume that the nonlinear system will be linear in that RKHS, because sometimes we cannot derive the linear system, but we are going to apply linear theory. See, this is what we mean by linearization. And the advantage of working in reproducing Kernel Hilbert space is that they allow to find a nonlinear version of algorithms that can be expressed in terms of inner products. So the outline is as follows. We are going to talk a little bit about learning theory in reproducing Kernel Hilbert spaces, and particularly function approximation in reproducing Kernel Hilbert spaces, and embedding of probability measures in reproducing Kernel Hilbert spaces, and how to find the difference between probability measures embedded in reproducing Kernel Hilbert spaces, which is what we call the maximum mean discrepancy. And then we'll apply these tools to the detection of critical transitions for some slow, fast SDEs. Then we'll talk about the approximation of nonlinear control systems in RKHS using tools of linear control systems theory. And then we'll talk about how to estimate the stationary solution of the Fokker-Planck equation of nonlinear SDEs using linear estimates. Then we'll talk about the construction of Lyapunov functions in reproducing Kernel Hilbert spaces, and finally, approximation of center manifolds in reproducing Kernel Hilbert spaces. So the summary of the approach is as follows. So we assume that there is an embedding from Rn into H that maps the variable x into z. And then H is reproducing Kernel Hilbert space. And then in H, we are going to perform an analysis. In general, it is a linear analysis, but it's not necessarily linear in some cases. And then we come back with the answers from H into Rn. So the transformation phi is obtained from the kernels that define the RKHS. So in general, it's not necessary to explicitly define the phi. And in practice, we are going to use a mapping that is constructed from the data. So k is a function of two variables. The second variable will be the one that is based on the measurements. So here, essentially, the measurements are going to be used to construct a Hilbert space where computations become simpler. So it's just to schematize what's going on here. So as I said, we have system sigma, and that is in Rn. So we have some question about it, and from there we are going to construct an embedding from Rn into H. So that's the phi is coming from the samples. And from here, so that we are going to get a different system sigma tilde. We are going to ask the same question. Then we come with an answer. So here we can apply linear theory, as you said. As I said, it's not necessarily linear theory. So this one I'm writing it between quotes. It can be nonlinear theory, because the linear theory in general applies in the infinite dimensional case. So since we are not going to have an infinite number of samples, then applying exactly the linear theory will not work. So there will be some residual terms that we have to deal with. And then from there, we are going to come back to Rn with answers about sigma. So this is for sigma, and this would be an answer about sigma tilde. So here is an example of just how nonlinearity can be dealt with by going into higher dimensional spaces. If you consider nonlinear polynomial in R, so if you consider the map from R to R3 that takes x to 1x x squared, then P of x becomes affine in phi of x. So what are reproducing Kernel Hilbert spaces? They appeared in the 30s as an answer to the question, when is it possible to embed a metric space into a Hilbert space? So the goal here is it possible to flatten a nonlinear space, and then by going to higher dimensions? So if we are working in some non-trivial space, can we apply linear tools to it? So this is why the original question was asked. And the answer is that if the metric satisfies certain conditions, it's possible to embed a metric space into special kind of Hilbert spaces, which are called reproducing Kernel Hilbert spaces. So properties of RKHS have been studied a lot in the 50s and later on, especially the work of Aaron Jan and Schwartz. And so what are they? So before anything else, as we said, these are Hilbert spaces with the following properties. First, that the kernel, which is a function of two variables, has the reproducible property. So the reproducible property is very important because it allows us to evaluate functions. So this is why we can we can construct a Hilbert space where we can do mathematical computations based on samples. And the second property is that the span of the kernel is dense in H. So in other words, the reproducing Hilbert space is a Hilbert space with a reproducing kernel whose span is dense in H. And an equivalent definition is that it's a Hilbert space of function where all evaluation functionals are bounded and linear. So important properties of reproducing kernels is that the RKHS is unique, kernel is symmetric, positive definite, and we have the following property is that kxy can be written as follows, which is exactly the question: when can we embed the metric space into Hilbert space? So k can be viewed as a metric, and then here this is coming from. We are essentially interested in writing something like this. And then by using this decomposition, you can get immediately that the easiest between the canonical feature map is given by the following x, phi Cx, which is kx dot. So this is the equation that we had, kx dot ky dot. So you get the phi Cx. So and then Mercer kernel, if we add the continuous constraint on the kernel, we are going to get something called the Mercer kernel. And this, the fact that Mercer kernels are positive, definite, and symmetric reminds us of similar properties of Gramians and covariance matrices that we are going to use in the following section. So here, examples of kernels are monomials, exponentials, and hyperbolic tangent. So one way to find another way, so we talked about the Aron-Jan canonical feature map. Another method to find the feature map is by considering the integral operator associated to the kernel. And from there, we are going to compute the eigenvalues and the eigenfunctions, which will give us the following decomposition of the kernel. And so this representation will give us immediately that the phi, which is the embedding, is something like the square root of lambda j psi j. So since lambda is positive, you can write it down as square root of lambda j psi j x times square root of lambda j psi j x prime. And so this will be similar to this decomposition here, phi x, phi y. And from there, we get the embedding, which is square root of lambda I psi I of x, where lambda I are eigenvalues of the integral operator, and psi I are the eigenfunctions. So the problem here is that it's not easy to find phi because it depends on the measure, and it's difficult to compute. So we are going to stick to Aron-Jan canonical feature map, which was given by kx dot. And these are like examples. As I mentioned, it's not necessary to invoke Mercer theorem, just for discussing feature maps. And these are examples of non-Mercer feature maps. For example, in the case of a monomial of degree 2, or the Gaussian kernel. So RKHS are useful in function approximation. So if we have a function f from x into y from random samples xi, yi, so we have the samples and we want to find the best estimate of f. So we are going to minimize, set up a criterion that we want to minimize. So this would be the formal solution of the approximant, except here that we don't know rho and we don't know f rho, so it's hard to compute f rho and e. And so we are going to discretize the problem, and then we are going to perform a minimization of the approximation in the RKHS. So lambda here is a regularization parameter. And the solution of this problem is going to be sum of Cj kx xj, which is Cj phi j of x, where phi j is Aron-Jan canonical feature map. And so we see the linearity here. So we are getting a linear solution of the problem in terms of the phi j, but also the Cj's themselves, they satisfy the following system of linear equations in Cj that is constructed from the samples. So learning here in this context is the process of approximating the unknown function from random samples on Z. So so here one of the things that we are going to use a lot is the empirical kernel matrix, which is given by kxi xj divided by m. And then we'll have the restriction operator that takes us from hk into rm, and then the adjoint that takes us from rm into hk. So now there is another application of RKHS in change point detection, where if we have a sequence of samples x1 to xn on a domain x, so we are interested in detecting a possible change point tau, such that before tau the samples follow a probability distribution p, and after tau the samples follow probability distribution q. So what we are going to do here is that we are going to map the data set into an RKHS, then compute a measure of discrepancy delta n. So this delta n will be small if p is equal to q, and large if p and q are different. So here the metric we are going to use is the maximum mean discrepancy, which is defined by the following expression. And essentially it's just the difference between the means of the probabilities embedded into the RKHS. So here what's going to happen is that we are going to take probability measure p and then map it into an RKHS. So this is what we call the kernel mean embedding. And the difference between the means in the RKHS is what we call the MMD. So nice thing about it is that you can express it directly in terms of the kernels, and we don't have to work in the RKHS. You can work directly in Rn. So this is one of the advantages of working in reproducing Kernel Hilbert spaces, that you don't have necessarily to go into higher dimensions. You can still compute things in the ambient space using the kernel. So you see, when you see K, it means that we are working in Rn. If you see phi, then it means that we are working in H. So this MMD is pseudometric on distributions in the sense that it satisfies all the qualities of a metric except that it's not equal to 0 only if P is equal to Q. So we can have other things happening. So for it to be a metric, it's sufficient that we have a characteristic kernel, i.e. that the map from P to H is injective. So this is what's going on. As I said, we map P into H, then we get the kernel mean embedding, and then we compute the difference between the means, and this will give us immediately the MMD. So a nice thing about the MMD is that if we are dealing with characteristic kernels, then the convergence in distribution is happening if and only if there is convergence in the MMD. And it can be computed directly from the data using the kernel. So if we have two IID samples, x1 to xm from P, and y1 to ym from Q, then an unbiased estimate of the MMD is given by the following expression. So modulo square, so this is MMD square. So you just have to compute this quantity, and then you would get the MMD. So in other words, so it's an integral probability metric that can be computed directly from data without having to estimate the density as an intermediate step. So okay, so let's apply these tools to the dynamical systems. So first we are going to talk about the problem of detecting critical transitions from some multi-scale systems. So here we are going to consider 2D fast flow SDEs, which have the following form. And so there is a critical manifold that is defined by f1, x1, x2 is equal to 0. So here, for example, we are going to focus on this particular example, but we have a theory for this entire class of systems where we can show that the MMD is maximal at the critical point. So if we consider the stochastic van der Pol system, so there is a periodic reset. For example, here, if we consider the following simulation, so we have critical transitions here. And then what we are going to do is that we are going to use the MMD for this case. So since we have only one signal, what is the x and what is the y? We are going to have a sliding window that we are going to divide into two parts. The first part will be the x, and the second part will be the y. And so we are going to compute the MMD between the first and the second part. So we're going to slide it, and then when we show that when we hit the critical transitions, the MMD will be maximal as illustrated in this representations. So other application is the problem of approximation of control systems in reproducing Kernel Hilbert spaces. So here we are going to apply really linear theory in this for this system. So in some sense, for this problem and the next one, we are going to view linear theory as a paradigm to analyze nonlinear systems in reproducing Kernel Hilbert spaces. So we consider a linear control system. X dot is equal to ax plus bu, and y is equal to cx. We assume that AB is controllable and AC is observable, and that A is stable. So we define the controllability and observability gradients for this linear systems. So these two matrices can be viewed as a measure of controllability and observability of the system. So essentially, if we consider the path energy LC x naught defined as the minimal energy required to reach x naught from 0 in infinite time, so this will be LC. And then if we consider the future energy defined as the output energy when generated by releasing the system from its initial state x naught with 0 input, we are going to get the following energy. So in the linear case, these two energies, they are characterized by two matrices, WC and WO. that satisfy two Lyapunov equations. So LC is equal to half of X transpose WC minus 1 X naught, and LO is half of X0 transpose WO X0, with WC and WO satisfying set of Lyapunov equations. So Gramians have many applications in linear control theory, and for example, if we want to perform model reduction, we can use them using by applying the method of balancing. So the goal here is that we are interested in representation of the system where we are interested only in the states that are most controllable and most observable. So this would be the ones that are the most important in the input-output behavior of the system. The states essentially that require a lot of energy to be reached or that do not generate a lot of energy at the output will be viewed as not important. So we are going to eliminate them. And so how are we going to find this kind of states? We will consider a representation of the controllability and observability Gramians where the WC and WO in this state space representation are equal, and then this will give us a measure of the controllability and the observability energies. So we are looking essentially for a transformation T such that TWC T transpose is T minus TWO T minus 1 is equal to sigma, and then so this will be a diagonal matrix, and if there is a gap in that matrix, so if there is a k such that sigma k is much greater than sigma k plus 1, then the states that are most responsible for governing the input-output relationship are x1 to xk. So how to find T? Here there are many methods, but the one we'll be using in the nonlinear case is by considering the Cholesky decomposition of WO. So we get a matrix Z, then compute the SVD of U of Z transpose WCZ, and then get T is equal to the following thing. So these are the things that we are going to use in the nonlinear case. So nonlinear case. So there have been a lot of results on how to find LC and LO from analytically speaking. So essentially, LO satisfies the Lyapunov equation, and LC satisfies Hamilton-Jacobi-Bellman equations. So these two equations are not easy to solve in general. So there have been some approaches where one is using Taylor series expansions or using statistical methods. So we are going to, but none of them gave like very precise results. So what we are going to do is to propose to work in this paradigm where we are going to use the method of linear balancing in the RKHS, and then from there get a solution of an approximation of the nonlinear system. So WC in the linear case analytically are given, and WO are given by the solution of the following set of Lyapunov equations. From data, so there is an approach, and this is what we are going to use essentially. So we excite the system with the impulses from the input with zero initial condition to get the controllability Gramian, and then excite the system with impulses from the initial condition with zero input to get the observability Gramian. And then from there, one can get, from these responses X and Y, one can get WC and WO. So so instead of working with this integral, we are going to work with their discretizations. And so how to do that for the nonlinear case? We are going to use the same philosophy, which is mapping the data into an RKHS and then apply the linear method of balancing there. So what happens here is that we have a system x dot is equal to fxu and y is equal to h of x. We assume that the method of linear balancing can be applied there. We now, in a linear case, that LC is given by half of x0 transpose WC minus 1 x0, and LO is half of x0 transpose WO x0, which can clearly be written as an inner product. So LC is an inner product of x0 modulo weight of WC, and similarly for LO. So here, if we map the x into h phi of x, then we can try to force the following estimates that LC is equal to half of WC pseudo inverse H. So this would be for the nonlinear case, inner product with H, and same for LO, WOH H. So this would be the estimates that we are going to impose. But somehow there are, of course, a lot of complications because we'll be working in infinite dimensional space. So we are going to use the restriction operators and its adjoint to get a kernelized version of the estimates. So LC hat, we can write it down as the following form after some work. So we get KCX, which is the empirical kernel matrix, Kx x mu. So these will be the measures. So you see, this is very similar to the embedding that I was talking about here. So the Kx dot, so it shows up here. So this will be the embedding here. And same thing on the other side. And then Kc is the general empirical Gramian. And similarly for LO, we can play similar games with the restriction operator and its adjoint to get an estimate of KO, of LO hat in terms of KO, which is same. It's a different space. So you see the different embedding where the second part is coming from observability samples. So the approach here would be the following, is that we have a nonlinear system. We apply the method of linear balancing in the RKHS. Then we perform balancing in the RKHS, like a linear balancing. And then once we are there, we can come back to Rn from H by getting a nonlinear reduced order system with a nonlinear mapping for the model reduction. So this would be, for example, in the case of the linear Gramian in Rn, this would be the WC hat, as we saw before. Then it becomes a covariance operator in the RKHS, and same thing for WO versus observability Gramian in the RKHS. So what happens there is that we construct the contrariability Gramian, the empirical contrariability kernel in the RKHS, and same for the observability. So this would be very two large matrices. So we perform the SVD for this object here, and then we use the aligning transformation, use the expression in the linear case to get the T. Then once we get the T, so we look for a spectral gap in the sigma in the RKHS, and then we disregard the ones that are small. And then once we get the model reduction in the RKHS, then we come back to RQ, which is the reduced order system in the ambient space. So this would be the nonlinear reduction mapping for the in RQ. So let's consider just this following toy model. So the 7-dimensional system. So we do the same thing. So we excite the system with impulses from the initial conditions with 0 input, and we do the same thing for the other one to get the KO, which is impulses from the initial from the input with 0 impulses. And then we simulate for different input, both the full order system and the reduced order system. So the 7 is this one, so the red one. So here we used 1,000 samples, and here we map the first 100 singular values in the RKHS, and we see that there is a gap between the second and the third one of order 100. So we are going to deduce that there exists a second order system for which we can that approximate the original system. And so then we are going to simulate it with different input, and we get the following results. So here, so essentially for this system here, the approximation will be a series expansion with several terms. So it's not easy to find a formal expression, but we are going to get something that is in the computer. Next section is about SDEs in reproducing Kernel Hilbert spaces. So same kind of thinking, where we are interested in analyzing nonlinear SDE. So we are going to view a nonlinear SDE as a nonlinear control system that is excited with white Gaussian noise from the input. So we write down the Fokker-Planck equation, and then we are interested in the stationary solution of the Fokker-Planck equation directly from data. So in the linear case, we know that the transition density is Gaussian, and all we need here is the mean and the covariance to uniquely determine the transition probability density. So if the system is stable, mu is 0, and the covariance matrix satisfies the Lyapunov equation that reminds us of the equation that WC satisfies. So which is exactly the controlability Gramian. And what we are going to notice is that the stationary solution of the Fokker-Planck equation, that is the steady state probability measure, is proportional to exponential minus LC. And this is where our estimate of LC from data will play a role in estimating the stationary solution of the Fokker-Planck equation for nonlinear SDEs. So even though this relationship here is valid for linear and some Hamiltonian systems, by embedding a nonlinear system into suitable RKHS, we may reasonably extend this connection to a larger class of nonlinear systems. And so this will be the assumptions here, that we have a nonlinear SDE, and we assume that in the RKHS, in the infinite dimensional case, that this nonlinear SDE becomes an OU process in H. Second assumption is that the push forward of the invariant measure of the original system is the invariant measure of the OU process in H, and that the push forward of the invariant measure admits a density. So essentially, this is what we are trying to get. So we have so here for all the work we have a lot of estimates that are that we derived. I just wanted to be as general as possible, in order to survey the results. But I refer you to the papers for the analytic results. So let's look at this following simple example here. So this is a double well potential in R, but by using a linear estimate, where we assume it is Gaussian in the RKHS, and whether there is only one bump, we could recover the two bumps in R. Other part is the construction of Lyapunov functions from data. So the approach is that we are going to consider nonlinear ODE x dot is equal to f of x. We assume that f is not known, but we have samples. We approximate f from x of ti. So the two previous problems, we adopted this philosophy of RKHS as linearizing spaces. For the next two problems, we are going to adopt a more direct approach, where we are not using this assumption of linearizing spaces, but it's just to illustrate the different approaches. So approximate f from x of ti, then we find the Lyapunov function v hat for f hat, and then we prove that v hat is also a Lyapunov function for f. So we are dealing with the following ODE. So x dot is equal to f of x with initial condition xi. So 0 is going to be an equilibrium point where we assume that it's exponentially asymptotically stable. So the Bassin of attraction is given by the following expression, and then it's directly related to the level sets of the Lyapunov function. So so we know, what is the Lyapunov function? Essentially, it's a function, the positive definite function that satisfies the Lyapunov equation, such that the orbital derivative is strictly negative if we are dealing with asymptotic stability. And then the sublevel sets of V are going to be directly related to the Bassin of attraction of the original system. Yeah, so now always the key has been how to solve the Lyapunov PDE. So there is an interesting result by Bhatia that says that we can we can impose the right-hand side. So essentially, Lyapunov equation is a differential inequality. But if we impose the right-hand side as a negative definite function, here it's minus norm of x squared, but in general it's p of x, where with p is the negative definite function that satisfies certain conditions, we can construct a Lyapunov function iteratively. So that's essentially what Peter Giesel did. So he said that we are going to find an approximation of the Lyapunov PDE by imposing the right-hand side. So LV of x is equal to minus p of x, with p is a strictly positive definite function. And so with p here, satisfying the following conditions here. So what happens is that we impose the right-hand side on the differential inequality in the Lyapunov equation, and assume that V1 has the following form. So essentially, if we consider phi to be some Wendland function, which is essentially a kernel with compact support, and we have a differentiation operator. So here, delta xk circle L, so composition with L. So this is differentiation with respect to L of the kernel. Then evaluation at xk, we get an ansatz for the solution of the Lyapunov equation. Then this will reduce to find, so here the problem would be to find the betas. So to find the betas, one has to satisfy also a system of linear equations. So we are going to get also a system of linear equations when working in the RKHS. So finding the V is essentially linear, but then finding the F is a different thing. So so once we get this V for the minus P, so when we impose the right-hand side of the differential inequality, it has been shown that the resulting solution of the PDE is also Lyapunov equation for the nonlinear system, and this is an estimate of the difference between the two orbital derivatives. So the goal here is just to extend this entire framework to the case of where we have samples where we don't know the F. So what's going to happen is that this approach, we are going to assume that we don't know F, but we know samples which are corrupted by noise, and so xi, yi. So to find the F, we are going to use the results that we got at the beginning and from the balancing thing. So we got estimates there that we are going to use here. And then we are going to show that the Lyapunov function for the F hat will be also Lyapunov function for the original system. And then we are going to work in a particular kind of reproducing Kernel-Hilbert spaces that are also Sobolev spaces because of the differentiation. So this is just an example to illustrate the method. So we consider the following nonlinear system where we now actually the Lyapunov function exactly. So x1 square plus x2 square. So first we use the samples to find an estimate of the F. So F1 hat and F2 hat from samples, and then we construct Lyapunov function for the approximation of the system, and then we get Lyapunov function for the original system. So here this is the V for with 360 points. This is for when we increase the number of points. The orbital derivative becomes sharper and by increasing the number of points. So we effectively get Lyapunov equation, Lyapunov function. And the last part is center manifold approximation. So here we are interested in detecting, in computing invariant manifolds from data. So we consider a nonlinear dynamical system x dot is equal to capital F x plus F bar. We assume that the system, so that F of 0, the origin, is an equilibrium point. So the goal is to analyze the stability of this equilibrium. So if all the eigenvalues of F have negative real parts, then the origin is asymptotically stable. If some of them are positive, then the origin is unstable. And then there is a critical case where some eigenvalues are with 0 real parts and the other ones have negative real parts. So here the linearization test fails, and we can use change of coordinates to split the system and write it down as follows. With F1 has eigenvalues on the imaginary axis, and F2 has eigenvalues with the negative real part. So intuitively, we expect that the stability of the full order system to depend only on the reduced order system, which is the x1 part, because the x2 will converge to 0 quickly, and this is what is the objective of the center manifold theorem that tells us that there exists an invariant manifold x2 is equal to theta x1, and that theta satisfies the following PDE that we obtain by plugging this expression into this system of ODEs. And the center manifold theorem ensures that there are smooth solutions of this PDE. And so what we want is essentially to find an approximation of this PDE from the samples. So here the center dynamics will be x1 dot is equal to f1 x1 plus f1 bar x1 theta x1. And so once we get the theta, then we can conclude about the stability properties of the full order system from the reduced order system. So what we did is that we used kernel methods to approximate the theta modulo modifications, because since we are going to be around the invariant manifold, that we are going to put some weight to emphasize more on the data around the origin. And because of the constraint that the theta satisfies, then we had to modify the representer theorem to include derivatives in the representation of the approximant of the function. So we consider the following. This is to illustrate the example, the concept. We consider the two-dimensional system where we now analytically there is an approximation of the center manifold as y is equal to minus x squared. So we used two kernels. One is the quartic kernel, and the other one is a Gaussian kernel, and both of them work to approximate the center manifold. So to conclude, so we used the maximum mean discrepancy as a metric to detect critical transitions of some slow fast SDEs using data directly. We also introduced estimators for the contrarity and observability energies, which are essentially solutions of Lyapunov equation and Hamilton-Jacobi-Bellman equation from the samples. So we use this to perform model approximation of nonlinear systems using a linear technique. And then from there, we got an estimate of the stationary solution of the Fokker-Planck equation for some nonlinear SDEs. So these estimators were all derived using linear methods. And this illustrates that the statement that RKHS act as a linearizing space even for dynamical systems. So we know that we're producing Kernel Hilbert spaces, which essentially are viewed as the most useful Hilbert spaces in machine learning, because they allow us to apply linear methods there in the static case. And here we are illustrating the same philosophy, that RKHS act as linearizing spaces for dynamics. And we also introduced a database approach for the construction of Lyapunov functions and center manifold approximation. And all these results, collectively argue that working in reproducing Kernel Hilbert spaces offers tools for database qualitative theory of nonlinear dynamical systems. So the interface, to work at the interface of dynamics and machine learning, it's nice to have a space where the two are interacting. And so this work shows that RKHS are a good framework for this kind of work. And finally, these are some references. We had the same issue of having problems to publish our paper. So this one that we published in 2010 in a conference, a short version. It took it 7 years to appear in a journal. This one took it like 5 years, and etc. So we had the same issue as the first author and the first speaker in this morning. Yeah. Okay. Yeah. Thank you.